Hello, I'm Adrian Hopgood. I'm Professor of Intelligent Systems at the University of Portsmouth. I'm also Director of the Interdisciplinary Theme of Future and Emerging Technologies and Director of the South Coast Centre of Excellence in Satellite Applications. I've entitled my presentation today, Introduction to Artificial Intelligence. It's a reworking and update of a presentation that was previously entitled Beginner's Guide to Artificial Intelligence, which I presented at the AI 2019 conference in December 2019 at the University of Cambridge. The presentation will be in two parts. In the first part, I will introduce artificial intelligence. I'll then go on to describe knowledge-based systems, which are a very explicit, textual, logical way of representing knowledge and expertise in a computer system. I'll then move on to talk about machine learning, which is a data-based approach, learning patterns in data. And the main technique there is neural networks. And then I'll also move on to describe deep learning, which is essentially large neural networks. In part two, I will introduce genetic algorithms, an important technique for optimization and finding the best combination of parameters for a wide range of problems. And then I'll move on to building practical AI systems by using the range of tools available in the AI toolbox. The slides for this presentation today are available at my website at adrianhopgood.com/presentations. So let's start with a question about what is AI. So normally, if this were an interactive classroom type setting, I'd be posing that as a question to the audience to see what came back. On this particular occasion, I think maybe I'll just imagine that I'm posing the question. And typically the answers that I get back would be something like, maybe some people would say it's machine learning with large data sets, which I think is part of the story. Others might say it's to do with mimicking human behaviors, which I think is closer to the original traditional definition of AI. So here's a very classic definition of AI, which is mimicking human mental faculties with a machine, with a computer, you might say. But that definition in itself poses some questions. So are you just interested in the outcome of your AI system, or does it need to work like a human? And of course, are we limiting ourselves too much by saying it's mimicking a human? Because with a lot of AI systems, you actually expect them to exceed human capabilities, not least in terms of speed. There's the issue about explaining itself. Does an AI need to explain itself? Is animal intelligence relevant? Quite a lot of people are interested in animal behaviors, and it all comes under the general umbrella of AI, which leads on to the question about whether biologically inspired computing is a form of AI. And there are no right answers to all of these things. So there are many different definitions of AI, but this is the general flavor. I guess another aspect about AI is that it's constantly moving on. So this is a quote from Rodney Brooks, one of the AI pioneers, who sounds a little bit frustrated in this quotation. He says that every time we figure out a piece of it, that's to say AI, it stops being magical and we say, oh, well, that's just a computation. So in other words, people are constantly thinking of AI as something new and different and better than what we currently have. And some examples of that might be that back in the early days of AI, chess was one of the big challenges. But then that was effectively solved in the 1990s when IBM's product Deep Blue beat a grandmaster at playing chess. Similarly, character recognition, so recognizing printed or handwritten characters, that was a major challenge. And in fact, I will use an example of that later in this presentation. But that's effectively solved, and I think it's a good example of AI that's actually out there in everyday use at the moment. So Royal Mail, for instance, is always using character recognition for reading reading handwritten envelopes, for instance. Speech recognition, likewise. So there is a kind of feeling that people are always thinking of AI as the next best thing, which can be a little bit frustrating for those who've, in the community, who feel like we've been actively developing AI tools. So a few considerations to bear in mind when using AI. Oops, sorry. So what is it for? You have to consider whether you're using AI to actually make decisions, so giving an AI system autonomy to do things of its own right, or whether you're using it more as a kind of recommendation system to give advice, or perhaps you're using it to processing and analyze your data. There are issues around trust with AI, quite a hot topic, in fact. And I think the key is to make sure that if you're using AI, you actually understand how it works. Part of that is understanding the context and the assumptions behind the AI, and hopefully you'll get some of that today. And explainability of AI is part of that. It's quite a big debate about whether AI does need to explain what it's doing. And then there are constraints around legal, ethical, practical issues, and indeed the availability of the data that you're relying upon. So a few broad considerations there around the use of AI. So I like to draw this Venn diagram of AI techniques to illustrate that actually this is quite a large family of different computer-based technologies, which I broadly divided down into knowledge-based and intelligence and computational intelligence. The knowledge-based intelligence tend to be quite explicit textual representations of knowledge. And there's a long tradition of AI based on knowledge-based techniques. So actually dating back to, certainly there was a great deal of activity through the 1980s in so-called expert systems, which were effectively providing expert advice. And those tended to use techniques like rules, case-based reasoning, model-based reasoning. I'll mention some of these techniques this afternoon. And the idea there was that they were very much to do with trying to capture the expertise of human professionals. So classic examples were in the areas of medicine, law, or maybe particular scientific domains as well. On the right-hand side, the computational intelligence side, these are more data-based. So what we're doing here is building systems whose performance is based upon making sense of data, often large quantities of data. And this is the area of AI that's really taken off in recent years and generated a great deal of interest. So I've listed their operational research, has quite again a long history to do with using mathematical techniques to find optimal or near optimal solutions. Neural networks, which have been around as a concept for a while, and there was a particularly useful generation were developed during the 1980s, and I'll say more about that shortly. And then more recently, these so-called deep learning algorithms, which are effectively just large neural networks, have really sort of, I think, been a major driver for the current interest in artificial intelligence. But I'm also going to touch today on genetic algorithms, see how they fit in, which are another technique for finding optimal solutions. And then I've put some techniques like fuzzy logic and Bayesian updating in the middle. I'm going to explain those shortly. But they're techniques that I think capture elements of both. They do capture explicit knowledge, but there's also a mathematical model behind them as well. So that's the broad toolkit. I'm very passionate about using the whole toolkit, and we'll sort of, as I run through some of the main techniques today, towards the end of the session, I'll highlight the use of these different techniques together. So let's look at a bit of history going back. So 1956, I've put up this poster for the film Forbidden Planet to illustrate the idea that sort of intelligent human-like beings have been, artificial intelligent human-like beings have been um, of interest in the world of fiction for many years. So Forbidden Planet featured this character, Robbie the robot, a humanoid robot, um, intelligent. I know it's somebody saying they're a great film, intelligent robot that people could empathise with. 1956 was also the year of the first published use of the phrase artificial intelligence. So the Dartmouth Conference in 1956 was specifically a gathering of experts to discuss artificial intelligence. So the topic's been around for a while. You might be forgiven for forgetting that in the current great excitement about AI. And in fact, you could perhaps trace it back 6 years earlier to 1950 um, with the classic paper by Alan Turing, where he proposed a test for whether a computer was displaying intelligence, what we now call the Turing test. He called the imitation game, to see whether it could fool you into thinking it was a human, or you couldn't tell the difference between a human or a computer. So AI has been around for a while, and so has the fiction. So on the right hand side here, you see the Asimo robot from Honda. That is real. That's not fiction. On the left hand side, there's a still from a film called Robot and Frank, which features a robot remarkably similar to Asimo, and that robot is Frank's carer, looking after him, and that's all sort of set in the near future, and you can envisage that we're pretty close to that sort of thing being a reality. So I think, broadly speaking, you can draw a spectrum of intelligent behaviours, where I've drawn a spectrum representing increasing levels of understanding. So at the very low levels, we have machines that can control reactions and regulation and coordination. And we've had examples of that since the 1970s with automated assembly plants, as you can see in that picture there. Right through to at the top, these areas of specialist expertise and so-called expert systems that I mentioned earlier, and I'll mention them again in the next slide, really try to capture that specialist expertise in narrow domains. And perhaps what's slightly counterintuitive is that the areas that have proved most difficult to build into a computer system have been the areas in the middle, which we humans can do with barely a conscious thought. Things like language and common sense, perception. Common sense meaning sort of adapting really to new situations in a sensible way. Vision and perception. All these things that we do, as I say, without specifically concentrating upon them, are actually the most difficult areas. But I think AI, to a greater or lesser extent, has now bridged the whole of this intelligence spectrum. But if we go back to some of the early days, some of those early successes were in these expert systems, these very explicit representations of knowledge. So going back to the 60s. So I've had a request here to annotate the content. I don't know what that meant. Carrying on. So Dendril was a system for interpreting mass spectrograms, Mycin for diagnosing blood disease, Prospector for prospecting for minerals. So quite specialist, narrow domains which were quite successfully encapsulated within a knowledge-based system. And these things are still relevant today. So more up-to-date examples include SmartGov for configuring websites for local government, and SeisExpert, which is a more kind of up-to-date version of Prospector in a way. It's using seismic data to interpret the geology. But as I say, some of the more tricky areas are around perception. So, and if you look at this photograph, which I was very proud to take in my garden, you sort of start to get a sense of that. So if you look at that image, and I'll talk a little bit later about neural networks for interpreting images like this, it's actually not straightforward at all for a computer system to recognize what's going on there, even if you can relatively easily build a computer system that encapsulates sort of key areas of expertise around the law or government. So what you've got here is an image which actually contains three rabbits, two live ones and a stone one. Uh, there's a pet rabbit in a cage and a wild rabbit in the foreground, which has come to visit on that particular occasion. That's why I captured the moment with my camera. But those three rabbits are in different orientations, different sizes. The pet rabbit is partially obscured. You've got some other things going on there. You've got a few flowers in the image. Quite a lot for a computer system to recognize. And not only that, you've got issues of context. So here's an image which features a tank, but it's not a tank in any kind of military threatening domain, any military threatening context. This appears to be some sort of publicity stunt, actually, with civilians on top of it, and it's going past the Houses of Parliament in London. So, so if you're building a system that recognises tanks, you've got an extra layer of challenge there to actually layer some context on what's being interpreted. So I mentioned that there's quite a lot of interest in AI at the moment. I might want to reflect on why that is, given that, as I said, we've been talking about AI since 1950 or arguably 1956. Well, I think part of the reason is maturing ideas. So a lot of the ideas around AI have evolved slowly and become better with every iteration. I think there's the fact we're sitting on lots of data, loads of data, so that's a big opportunity to build systems which can exploit those data and find patterns within those data. Which leads on to the third point, which is deep learning. So there have been some significant strides in recent years in developing algorithms that can actually make sense of those large quantities of data. I think fourthly, there's the internet resources. So if you're building an intelligent system now, you don't have to capture all the knowledge within the system. There is a wealth of knowledge of variable quality available across the internet that you can tap into with your AI system. And perhaps most importantly of all, we've now got faster computers than we've had in the past. So ideas which were bandied around 20 years ago are now practical on ordinary everyday computers, whereas they would have been impractical or needed a supercomputer in previous decades. So I think those are the 5 key reasons why there's such a lot of interest at the moment. So I'm going to start, as I say, by talking about knowledge-based systems, and then I'll move on to neural networks before I have our tea break. So for me, the key thing about knowledge-based systems is that you separate out the so-called knowledge base and the inference engine. So the idea is that you separate those two aspects so that if you're let's say a specialist medic, you can put all your medical knowledge into a knowledge base in some kind of structured form, but you don't have to be an expert programmer. You don't have to understand all your and sort of fit it into nested control loops and so forth. The inference engine is the program which applies the knowledge that you've put into the system as and when appropriate. And there have been developments in the kind of environments in which you can do this, build these kind of systems. So here's a screenshot from a system called VisiRule, which I've played with, and in fact, if you have a copy of my book, you can download a free copy of VisiRule from via my website. There's a link there. It's all part of the Flex package from the Flex and LPA Prolog package available from LPA Limited. But the point about the reason I'm showing you this is actually an example for helping to recommend a solvent for a particular problem. And it takes into account what it is you're trying to dissolve, takes into account the ventilation, the sort of the containers that you're using, and so forth. But it's interesting that it has a sort of dual representation here. There's some code, looks like computer code in this box here, but equally there's a visual representation of it here. So if you're building this system, you can either build your visual representation or you can write the code. Each is equivalent to the other. And as I say, the main point is that you're putting that knowledge into the system, and the knowledge-based system, the inference engine of the knowledge-based system will apply that at the appropriate time. And there are two broad ways in which that's achieved, which are called forward chaining and backward chaining. I'm not going to go into these in great deal of detail, but the key point is with forward chaining is so-called data-driven. That is to say that the rules that you put into the system will be applied according to whatever data is coming into the system. So I'm going to show you in a moment an example to do with monitoring the state of a boiler. So according to whatever observations are made, rules will fire and a conclusion will be drawn just based on whatever rules are available within the knowledge base. Backward chaining is somewhat different. With backward chaining, you have a specific goal in mind, which in the current climate might be, for instance, to diagnose whether a patient is suffering from COVID-19. So you might seek information in your knowledge base, which will tell you whether that patient is running a temperature, whether they live with other people, if they do live with other people, whether any of those other people are showing symptoms. So there's a sort of backtracking through a trail of logic through other rules which might lead you to the goal. And as soon as you reach something which is definitively established, a specific fact, you can then sort of unfurl that logic from those proven facts that through to the goal that you're trying to prove. So with backward chaining, it's very much focused on applying the rules that through a chain of connection lead to the goal you're trying to prove. So here's a brief example of a boiler system, an industrial boiler system, which has got various things going on, and different observations that you can make. And this is described in a bit more detail in my book. But you might have some simple rules in your knowledge base. So so-called production rules have the simple form of if condition or set of conditions, then conclusion. So in this case, if the pressure is above 1 megapascal and the release valve is closed, then you might deduce that the release valve must be stuck. That's a simple rule, a so-called production rule. But you can overlay increasing levels of sophistication onto this sort of thing. So so there's quite a lot of work around uncertainty, and I will be saying some more about this shortly. You might have exactly the same rule, but say that given those conditions, the release valve is probably stuck with a probability of 0.6. So that's a degree of uncertainty associated with the rule itself, but you may also have uncertainty associated with the conditions as well. So it's quite an involved area, and I'll say a bit more about that in a minute. But here's an example of some further production rules, and this uses the flex syntax that I mentioned earlier. And these are rules about my fictitious boiler. If the temperature is high and the water level is not low, then the pressure becomes high. If the transducer output is low, then the water level becomes low, etc. And there's a link between these rules. So if rule 2.8 is applied, if we say the rule is fired, if that rule is applied, then the water level becomes low. And that means that the condition for rule 2.7 is now no longer valid. So because 2.7 has part of its condition that the water level is not low. So you see there's a dependency between the rules. So one rule enables or indeed maybe disables another rule. But the point that I keep coming back to is that the inference engine is the software, the program that applies the knowledge. And the idea is that the domain expert, in this case in the world of boilers, would be able to just apply their knowledge of boilers, add that information, and it would be applicable. Now, this is the only equation in the whole workshop is in this slide on Bayesian updating. I mentioned this idea that you might have a probability associated with a rule or the conclusion of a rule. And Bayesian updating is probably the best established technique for that. Been around for a long time, been around since Bayesian was developed in the 1970s, but still useful to this day, and a lot of work still going on using Bayes. The equation there is essentially Bayes' rule, which says that the probability of a hypothesis given some evidence is equal to this equation here. And what it's actually doing is turning a probability of a hypothesis given evidence into a probability of evidence given a hypothesis. And just to give a more concrete example of that, so a probability of a hypothesis given a piece of evidence might be that the probability, or how often there is an outlet blockage, that's your hypothesis, when a steam escape is observed, that's your evidence. Equally, the other way around, the probability of evidence given a hypothesis, which is generally easier to find, is how often a steam escape is observed, that's the evidence, when there is an outlet blockage. So putting things the other way around. But the key thing, you don't really need to understand that particularly, but the key thing about Bayesian updating is you have this idea that every assertion has a probability associated with it, and you update it in the light of new information. So if I go back to my rule 2.7, which in its simple form said that the temperature is high and the water level is not low, then the pressure becomes high. In its Bayesian form, we might say that each of these assertions, temperature high, water level low, pressure high, each of those assertions has a probability associated with it. And what you're doing with this rule, this Bayesian version of the rule, is updating the probability associated with the pressure being high. It's updated using these so-called affirms and denies weights. So if the temperature is high, you apply this kind of weighting to raise the probability of the pressure being high. Conversely, if the temperature is not high, then you can reduce the probability of pressure being high. This second condition is the other way around, in that the denies weight is higher. That's because if you look at its original form, it was a negative rule. So if the water level is not low, then that serves to increase the probability of the pressure becoming high. So you've got this concept of probabilities constantly being updated. That's the key message of Bayesian updating. And here's an example that I ran online, actually, as an illustration provided by Waltzman, with a light-hearted example about trying to predict what wine I might like to drink. So pose a series of questions about preferences and what sort of meal I'm going to drink. And I'm imagining, I don't think this was explicit, but I'm imagining it started off with a set of wines, each of which had a 50% chance of being my preference, and those probabilities were updated based on the information that went into the system. And based on that, the wine whose probability was updated to the greatest extent was Chardonnay. I don't think I'd have actually chosen the Chardonnay, but nonetheless, that's the principle there, that you're updating these probabilities. In this case, the probability that Chardonnay or Chablis or whatever is my preferred wine in the light of the incoming information. Let's move on to fuzzy logic, because that boiler example included some very vague terms, and like temperature being high, water level being low. And that's the gist of fuzzy logic. It uses vague language, but it does have an underlying precision. And the conclusion scales with the degree of satisfaction of the conditions. Excuse me while I'm finding my right slides. So to give that a bit of context, let's think of an explicit example. A very simple example, but in fact an example of where fuzzy logic is actually used in everyday life. So let's think of a digital camera like you might have on your phone. That camera adjusts the aperture size according to the light level. And you can capture that requirement into two simple rules. If the two simple fuzzy rules, if the light level is high, then the aperture should be small. If the light level is low, then the aperture should be large. That captures exactly what the digital camera has to do. And using just that simple pair of fuzzy rules, you could build a system to do just that. And the point is that there's a scaling here. It's not a sort of hard cutoff between the light level being high at one point and low at another point. It scales. So as the light level increases, the aperture becomes smaller. So it's a scaling response, according to scaling with the degree of satisfaction of the conditions. And there is some mathematics behind that. If we just look at this top pair of graphs at the moment, so here there's some fuzzy rules which are effectively saying that if the temperature on the left-hand side is high, then the pressure will be high, and if the temperature is medium, then the pressure will be medium. And what happens is that your conclusion is scaled according to the degree of satisfaction of the condition. So if we consider the specific case of temperature of 180 degrees in the context of this industrial boiler, that is considered somewhat high, about 75% high and 25% medium. So that scaling is carried across to the conclusion, where the corresponding pressure is considered to be 25% medium and 75% high, and you can defuzzify that to get a corresponding pressure. So that's the gist. So I see there's a question coming through. So what's the difference between likelihood ratios and a feedback loop in electronics? Well, I suppose there's a similarity there, except that I suppose that one is more broad. I suppose the Bayesian updating can be applied to a whole range of things, including information which is coming through from various different sources, including being directly entered by the user. But in a sense, you could say it's the application of feedback. So the current state of understanding is evolving as you go. So I've got a practical example of fuzzy logic which I want to show you, which is to do with monitoring an elderly person in their home to make sure they're okay. So this is an area of interest in general as we face an aging population. We want to make sure that people live a high quality life but are safe from harm. So what I'm going to show you in a minute is a kind of a video sequence that shows a depersonalized silhouette of a person, which is the so-called voxel, a sort of a volumetric shape, which has a centroid, its sort of central position, and a kind of horizontal alignment, which is to say whether the shape of the voxel is pointed vertically in a sort of standing position or horizontally. So we've got a couple of fuzzy rules here. The first one says that if the voxel centroid height is high and the horizontal alignment is low and the maximum height of the voxel is high, then the uprightness of this person is high and their likelihood of fall is conversely low. Looking at the rule the other way round, if the voxel centroid height is low and the horizontal alignment is high and perhaps the maximum height is medium, then the uprightness is low and the fall likelihood is high. And in this system, there was a set of some 30-odd fuzzy rules, a bit like this. And I'm just going to show you a short video sequence now to illustrate this. So I hope you can see that okay. What you've got here, on the right-hand side, you've got two video feeds, which I'm pointing to. And they're combined to produce this kind of voxel shape, depersonalized shape. And that's meant to make this system less intrusive so that you can't actually identify the person. And what you've got in the graph across on the left-hand side is this is the sort of moment in time, is the dashed line down the middle. So right now the person is considered to be somewhat down, so a high possibility of being close to the floor, and now they're upright, moving around. And you see there's this sort of so-called footprint of uncertainty, this green band around the person, around the graph there, illustrating a sort of level of confidence. So you can see as the person dips down, that's picked up in this fuzzy logic system. And there's a little blip there as the person bounces up a little bit. And finally, final thing I wanted to say on knowledge-based systems before we move on to neural networks is that we tend to think of machine learning very much in the context of data-driven systems like neural networks, so-called deep learning algorithms. But there is a tradition of knowledge-based systems which learn through experience, and I think the most classic example of that is case-based reasoning, which is very much to do with the way human professionals and specialists work. So when a car mechanic is faced with a problem, they would typically think about some previous problem they've come across in the past, see in which ways it's similar, adapt their previous experience, and then next time they encounter another faulty car, they'll have had this newer experience in their mind. So in the case of case-based reasoning, it's very similar. The system, faced with a problem, goes to look for previous experience, whether there are previous similar cases that have been stored. Then the most similar or the most relevant will be picked out to reuse. If that past example is an exact match and happens to exactly solve the current case, that's perfect, and then we have a solution. But more typically, it might need to be revised and refined for the new scenario, and then it can be applied to the new case. If that works, that's then retained in the knowledge base, the case base, for future use. So that's just a sort of small point to say that although we think of machine learning very much in the context of data patterns and learning patterns in data, there is this other side of it, this very explicit side of knowledge-based forms of machine learning, case-based reasoning being a case in point. So before we move on to neural networks, I'll pause at this point. So we've had a bit of an introduction to AI. There's been progress across the board towards human mimicry, which I gave as my sort of broad definition of AI. So Asimo is a real-life specialist robot, specialist form of AI, but it's still a long way short of Robbie, the fictional robot, which was quite generalized in its artificial intelligence. Mimicry is often not the goal. So often AI performs somewhat differently from humans, and you're actually just interested in a practical application. We talk of AI meaning artificial intelligence, and there's a kind of implication that it's sort of replacing the human, but in fact augmented intelligence is often an alternative where the AI is there as a sort of friendly advisor. And there are very many practical systems that we were going to cover in the course of this afternoon. So I'm going to just pause there for a moment before we look at neural networks. So put my video camera on again, just see how everybody's doing. Are there any questions? Everybody okay, or shall I move on to neural networks? Okay, I think we're good. So I'll pause my video camera again, and we'll start talking about neural networks now. So neural networks, they're effectively about pattern matching, finding patterns in data. And these are the real driver behind the current interest in AI at the moment, as I mentioned, this idea of deep learning and so forth. So what I'm going to do is introduce some of the more traditional types of neural network. Then I'll move on to some of the more modern, more complex types of neural network. And I'm going to try a couple of live demos as we go. So wish me luck with that. So broadly speaking, I think we can say that neural networks are essentially classifiers. So that's the bottom line. And we use that sort of classification for predicting, sometimes for clustering, and sometimes for so-called non-linear mapping, which is to say mapping one set of inputs into one set of outputs. But broadly speaking, they're classifiers. You look for patterns in data and say, yeah, that's one of those, or that's a class A, that's a class B, etc. We'll look a little bit about the link to biological neural networks, talk about training neural networks, and talk about a couple of specific types of neural networks today. So this is what a biological neural network might look like. So let's go back. So what a biological neural network might look like. Very complex networks of axons, neurons, all connected together in unimaginably complex ways. So the link to the artificial neural networks that we use in computer systems is tenuous, I would say. So that most artificial neural networks are inspired by the biological neural networks, but I think they're very much a pale representation in my from my point of view. So this is what a simple neural network, classic simple neural network structure looks like: a multi-layered perceptron, sort of workhorse of neural networks that came to prominence during the 1980s. Sometimes called a backpropagation network because of the learning algorithm within it, which is the backpropagation algorithm. But essentially nothing like the complexity that you've got in a biological neural network. So when people talk about the similarity to the brain function, you really take that with a pinch of salt. Just think of it as something that's loosely analogous. But the key point here is that you've got these set of simple neurons connected together. So in this multi-layered perceptron, there's a set of 6 input neurons, and all they do is send their output through to the first set of processing neurons. What the processing neurons do, I'll point to those in this middle layer here, this so-called hidden layer, the middle layer. What they do is they take the sum of their inputs, pass it through a simple function called the transfer function, and then send that out upwards towards the next layer, in this case the output layer. So all the neurons are doing is summing the inputs, passing it through a simple function called the transfer function, and sending it on its way. The key, though, is that each of those connections has a weighting associated with it. And by adjusting those weights, the neural network can be trained so that it associates particular sets of inputs with particular sets of outputs. Typically, for classifying, as I said, so that it would associate a particular set of inputs with a high value at output number 1 and low elsewhere, indicating class 1, or a high value at output 2, low value elsewhere, indicating class 2, and so forth. That's typically what they're used for. As I say, they're also used for things like predicting, but in a way, predicting is a form of classifying anyway. You're saying that if you're predicting a particular outcome, that's because you've classed the scenario as leading towards that outcome. There's a question online: is backpropagation the same as reinforcement learning? It's similar, but backpropagation is a very specific algorithm specifically designed for this architecture of neural network. Reinforcement learning sort of rewards performance in a sort of more general way. So there's, broadly speaking, two types of neural network training, so-called supervised and unsupervised. Supervised, probably more common, which is where you know the equivalent truth that you're aiming for. So in the case of classifying, you've got a set of examples where you know the corresponding truth for each of those, you know which class it belongs to, and you can explicitly train your neural network to learn the associations between inputs and the associated class. Unsupervised, you don't know the associated class. What you're actually doing is letting the neural network find for itself the clusters. So it's finding data that are in some way similar to each other. So it forms its own, it clusters them together into its own classes. You're not telling it what the classes are. So those are the two main broad categories of training methods in neural networks. But I'm going to show you some practical examples which will hopefully put some flesh on that. In terms of the unsupervised learning, a classic example again from that era of the developments of the 1980s is the Cahonan self-organizing map, which has this sort of structure that's illustrated there with many more nodes than I've put in this simple diagram. And like inputs tend to cluster in different parts of this kind of map here. So you'd get a clustering of firing neurons down here and a different cluster up here in a Cahonan network. But I'm going to give you an example now, which will hopefully make this a bit more tangible. I'm going to look at a classification example to do with land use and recognizing land use from satellite images. So here's a set of images, satellite images, all taken. It's actually effectively one image because what you've got here are 6 different frequency bands. So it's a way of representing a color image, except you're separating out the 6 different frequency bands of the color to give you six images. But all of exactly the same place. It's actually part of the Mississippi Delta in the United States that we're looking at here. And what would be good would be to use images like this to recognize what's down there on the ground, what the land use is. So for this specific case, we have some ground truth. This is what is actually down there on the ground. This is the corresponding portion of the ground mapped according to land use. And we've got 5 categories, 5 classifications: water, trees, cultivated, soil and rock, or swamp. And what I'm going to do is train a neural network to learn to classify land use based on the images. So what I'm going to do to test my neural network is I'm not going to show it the whole image. What I'm going to do is show it the top slither of the image in its 6 different frequency bands and the corresponding land use. I'm just going to show it that top slither, train it on that small piece of information, and then see if it can classify the land use for itself for the rest of the image, not having seen previously the rest of the image. That's the idea. And I'm now going to call up some software to show that. So bear with me while I find my genetic algorithm. Okay, hopefully you can now see a different image on the screen, which is my multi-layered perceptron, very similar to what I showed you before, in the sense that you've got a set of input neurons, input nodes here, a layer of so-called hidden neurons, processing neurons here, and output neurons here, which are also processing neurons. I've got 6 input neurons, which represent my 6 frequency bands of my input data. And I've got 5 outputs, which represent my 5 outputs categories. And before I run this, I just remembered that I did want to show you just a particular feature of the image, just so we can bear it in mind when we run the demonstration. So I'll just briefly go back to the slideshow. I just wanted you to bear in mind that that if you look at the top left corner of the image, it starts off with water, which is class 1, and then moves into swamp, which is class 5. If you can just remember that, that will be important when we run the demonstration. So what I'm going to do first is I'm going to train the neural network. Remember, I'm only showing at the top 1/16 of the of each of those images. Let's set it running now, and what you'll see in the graph box is the error reducing as it becomes better and better at classifying those example data. Okay, so you see this error is going down. What it's doing is it's adjusting the weights. Remember, there are these weights that connect the neurons. It adjusts those weights so it gets better and better at associating the inputs that it's presented with the corresponding outputs, the corresponding output classes. So I've now trained that on those on that narrow bit of the top 16th of the images. I'm now going to test it, and what I'm going to do is test it a pixel at a time, starting with the top left-hand corner. So I'm going to present across the 6 inputs that same pixel in each of the 6 frequency bands is going to be the input, and I'm looking for the output classification. If it thinks that the first pixel is class 1, we should see a high output here at this first output neuron. And that is exactly what I'm expecting, because you'll remember I said that the top left corner of the image was dark blue, which was my class 1 of water. I'm just going to test this now. Just going to present it with just the 1 pixel. And what's happened is it's produced a high output at class 1. So it has indeed said that top left corner of the image, that top first pixel is class 1. If I move to the second pixel, we should find exactly the same. Again, it's the same. And I'll do the third pixel. It's the same, producing. So it's the first few pixels are all class 1. Let me just run forward a bit now then. Go forward 10 pixels. And we might now start to enter the swamp region. We do indeed. We now see that the high output is class 5, which, as you remember, was the swamp region. So it's got those first few pixels right, and let me just do the neighboring pixel there. And the neighboring pixel is also swamp, as you'd expect. So just based on those first few pixels, it's getting it right. So you can build up the whole map by doing that pixel by pixel. So rather like in Blue Peter, I have done just that earlier. So I'm now going to go back to my presentation. Remember, this is what I've trained it on, just the first top 16th. And now let's see what's happened. That was the training data. This was the actual grand truth in the middle. And towards the right here, I'm presenting the results. This is what came out of my neural network classifier, just based on that narrow bit of training.
And from first glance, you would actually say that looks pretty good. It's got most of that right. It's not got it 100% right though. Oops, that's gone forward a bit. It's not got it 100% right. If you look here, you might see there's a little bit of water missing. If you look down here, there's rather too much red. There's rather too much cultivated land in its classification. But hopefully you get the gist that you've got something that's mostly right based on a very restricted bit of training data. So you should hopefully be starting to get the idea that if you've got a rich set of training data, many more training examples, and perhaps a more sophisticated neural network, which I'm going to show you shortly, then you've actually start to get something that's quite reliable at classifying and recognizing the data. I'm going to show you another example now because it sort of nicely sets up the need for some of these modern deep neural networks like convolutional neural networks. I'm going to show you an example which I alluded to earlier, actually, to do with recognizing handwritten characters. So recognizing handwriting is not straightforward. So here's some examples of the word technology written with people with different handwriting, and indeed even written in a sort of ransom note style here. Getting a computer system to recognize words and characters is not straightforward, but a neural network can have a key role. But in a task like this, if I was to simply present a bitmap image of those characters to a multi-layered perceptron, the kind of simple neural network that we've seen so far, it would rarely produce good results. The reason is that the neural network requires some sort of pre-processing. This type of neural network, I should say, a simple multi-layered perceptron, needs some kind of pre-processing to pick out the key features called primitives. So in the case of characters, the primitives might be the number of curves, loops, or lines in an image. So what I've done in this example, the multi-layered perceptron example, is to pick out the primitives using a particular well-established technique, which is to scan the character, this is character A, both horizontally and vertically, and count the number of black to white transitions. And that gives me this set of numbers down the left-hand side and across the bottom. The number of black to white transitions as I scan that bitmap. And now, instead of having a bitmap of several hundred values, which the neural network would actually struggle to make much sense of, I've now got a much reduced set of 24 values, which are quite descriptive of characteristics of the letter. So where you've got a kind of a loop in the middle here, you've got a 2, where you've got a particular leg of the image, here you've got 1. There is a particular point here where there are 3 black to white transitions because there's a little bit of a gap in the bitmap. So that's much more, that pre-processing extracts some characteristics of the letter. What I'm going to do now is run a simple neural network to see if it can recognize characters. And I'm going to make it quite a tough challenge, because what I'm going to do is give it quite a limited training set. I'm going to train it on 9 examples of handwritten digits, 9 examples of each of the 10 handwritten digits. And these are real digits from postcodes, actually, gathered by Professor Andy Downton at the University of Essex. Formerly of Essex, I should say. So I'm going to train a neural network on just the 9 examples and then test it on the one that I kept back, the one in a red box, a previously unseen example. So I'm going to go back to my neural network software and see how we get on with that. I'm going to open up a different network now. Just looking for my right network. Okay, so we've got this very similar to what we saw before. Exactly the same structure as before. We've got a layer of input neurons, hidden neurons, first processing layer, and a set of output neurons. Exactly the same structure. The linkages are not shown because there's so many of them in this screen it would become too cluttered, but they are connected, fully connected as before, and there are weights on the connections as before. We've now got 24 input neurons representing that's the 24 primitives that I've extracted from each character. And what I'm going to do now is train that network on the 9 examples of each digit. And as before, what it's doing is adjusting the weights so that it becomes better and better at matching us inputs to the corresponding output. But remember, this is a very limited training set, just the 9 examples of each digit. So let's see how it gets on. What I would expect if I present it now with the previously unseen example of the 0, then the 1, then the 2, then the 3, etc. I'd first of all expect a high output here, then a high output here, then a high output here, etc. So let's test this now. I'm going to just test it with the first character, which was a 0, and we've got a high output here, which is exactly what I want. So that's good. Now I'm going to test it with the next character, which is a 1, and I expect a high output here at this second node. And that's what I've got. So it's got the 0 right, it's got the 1 right. Let's move on to the 2. It's got that right, going well. Move on to the 3. Yep, it's got the character 3 correctly identified. Let's move on to the character 4. Ah, now it's got that wrong. It thinks that's a 9. I was expecting this node here to be high. Do the next one, which is a 5. It's got that one wrong as well. Let's move on. It's got the 6 right. It's got the 7 right. It's got the 8 right. And it's got the 9 right. So with this simple example, testing it on 10 previously unseen digits, it got 8 of them right, and it got 2 of them wrong. Go back to my slideshow. So that's, in my view, that's not too bad. Let's go back and look at what we were looking at. So essentially a very simple neural network trained for just a few iterations that you saw on your screen there as I was training it, just trained on 9 examples, actually became a reasonably good recognizer of handwritten characters. So if you imagine you had a much larger data set, and if you have a much larger, more complex neural network, you can design a pretty reliable recognizer of characters. So that's the point I wanted to make. And that's why it's actually quite helpful that they've got a couple of them wrong, because you do need to have a good training set. And you know, similar message goes with the land use classification. So where do we go from there, though? If you want to build a better and better neural network, so you could make it more and more complicated, so it becomes better and better in the training. But the trouble is you can end up with something that's overtrained. And my graphs here are meant to illustrate that point. If we start with the graph on the left-hand side, what I've illustrated here is a simple example where you've got 6 training points represented by those blobs. If you really wanted to learn the link between those X and Y values, you'd probably want to draw something like this solid line between them. And that's what a suitably trained neural network would effectively do. Your risk, if you put too much complexity into your network, or if you train it for a long period of time, is the overtrain. So it becomes better and better at identifying those specific training examples. But in doing so, it loses its ability to generalize. It becomes less efficient as a generalized classifier. And you can see that in this two-dimensional example here on the right-hand side, where we've got some examples of class 1 up here, class 2 here, class 3 here, and the overtrained neural network has become very proficient at identifying these in class 2, these in class 3, these in class 1. But you see how narrowly it's drawn its boundaries around those examples, so that if a new example crops up somewhere between these sets, so I don't know if hopefully you can see my pointer there, it's in sort of no man's land, not being clearly classified as class 1, and yet it should be. Clearly that top part of the image is belonging to class 1. The top part of the graph is belonging to class 1. So this is an example of overtraining. And this leads me on to convolutional neural networks, so-called one of the classic example of a deep learning neural network. So if we look at what we've seen so far, particularly with this character recognition, we've seen that I had to work quite hard to process the image in the first instance. I had to find those primitives. That was a certain amount of data processing before the neural network could even get going. And I also talked about the fact that if I built more complexity into that network, by building more nodes, more connections, and so forth, I would run the risk of making it overtrained. I wouldn't actually get benefit from that. On top of that, there's another downside in just adding more and more complexity to the sort of neural network that I've just shown you, and that's because all of the nodes are connected to all of the nodes in the next layer. You get a combinational explosion of the number of computations that are required. So convolutional neural networks came to prominence. I guess I think they were technically first discovered in 1998, but sort of become the real driver of deep learning from the 2000s onwards. And they overcome pretty much all these difficulties. So first of all, they effectively find those primitives automatically, so they remove that need for pre-processing of my image. They also overcome this issue of computational explosion of nodes and the associated overtraining by being more selective in which nodes are connected to which other nodes. And that connectivity, as it happens, is inspired by the design of the cat's visual cortex. So we come back to the earlier thing that neural networks are not a realistic model of the brain structure. Likewise, the convolutional neural network is not really a realistic model of the cat's visual cortex, but it borrows some of the inspiration from there. So let's have a look at what's going on with a convolutional neural network. So at the left-hand side of this image, I've put my familiar image of my 3 rabbits in the garden. Just converted to black and white for this purpose, but that's the original image. And what happens here is that I don't have to pre-process that. I can present this bitmap image to the convolutional neural network. I'll say a little bit in a minute about what these convolutional layers are doing, but effectively what they're doing is picking out features in the image. They're not providing any kind of domain knowledge. They do not know what these features are. It's just recognizing that there are features. So you might say there are these 3 rabbits. There's these 2 flowers. All the convolutional layers do is pick those out, recognize that those are features. Let's say feature 1, feature 2, feature 3, feature 4, feature 5. Pick those out. That's the key thing that's going on in the convolutional layers. Those are then passed at the final stages to a classifier, which is very much like what we've just seen in the multi-layered perceptron. That's the final stage. So it's only this final stage, the classification, that's domain specific, that's actually to do with, in this case, recognizing rabbits or flowers. All the earlier stages are to do with recognizing features. So they are quite general and applicable to a wide range of problems. So I'll come back to that point later, because it does mean that some of this training can be done in a very general sense, and only the last bit has to be specific to the problem at hand. If we look a little bit more about the structure, the input to the neural network is now two-dimensional, representing the bitmap. You have these so-called feature maps, which are the next layer up. So-called pooling, which is a way of reducing the number of connections. As I mentioned earlier, part of the achievement of deep learning is managing that complexity. And then finally, you've got the classification. Let me say a few more words about that, managing the degree of connectivity. So the way in which those connections are done, this is the input layer on the left. This is the next layer, the so-called feature map, the next layer up. If this were designed the same way as the multi-layer perceptron was, the idea of totally connected, then every node in this right-hand layer would be associated with every node in the left-hand layer. That is not the case with the convolutional neural network. What you actually have is little clusters of input neurons representing small parts of an image, so-called local receptive fields, are connected to a single neuron in the feature map. And the next neuron here, the neighboring neuron in the feature map, is connected to the next, shuffled along by one bit, the next collection of bits. So it reduces the degree of connectivity. Still a large amount of connectivity. This is still a lot of learning involved, but nonetheless, it's made manageable by this degree of selectivity of connection. So if we look a bit more about the general concept there of the convolutional neural network, it's inspired by the cat's visual cortex in the sense that it is not fully interconnected. The interconnections are those that mimic what's in the cat's visual cortex. You have this idea of layers of abstraction. So you move from features to a broader understanding of the image, and then finally classifying. And this sort of receptive field is picking out sub-regions in the original image. And I've also pointed about the clusters. And you're constantly, part of the design, as I say, is making the degree of connectivity more manageable. It's an important point that only the final classification stage is domain specific. And the reason, one of the key points about that is that it does mean that you have this idea that you can have pre-trained convolutional neural networks, which can be trained on any sort of image. Let me go back to this image here. So these convolutional layers could be trained on a wide range of images. It doesn't matter what they are, because all it's doing is learning to pick out features. It's only at the final stages that you're learning to classify those features. So what tends to be happening, another kind of efficiency that's put into these deep learning networks, is this idea that you can use something that's pre-trained on a data set that you don't know about, and it's only the final stages, which are domain specific, where you train it using supervised learning on your specific domain. So there are a few tricks going on there with this deep learning. It's deep in the sense that you've got multiple layers. It's deep in the sense that there are layers of abstraction. There's efficiency in terms of selectivity of the connections, which make this large neural network with very many nodes computationally possible, albeit computationally demanding, but it is computationally possible. And that's, for me, that's probably the most influential design of neural network at the moment, the convolutional neural network. But so I did want to finish this section by just briefly talking about a few other designs. There are many other designs of neural network. I'm just picking out some of the main ones. A lot of interest at the moment in so-called GANs, that's generative adversarial networks. And the idea here is that you have two neural networks sort of in competition with each other. You've got the generator and the discriminator. The generator is a bit like somebody who makes fake artwork, and the discriminator is a bit like the curator in a museum who's trying to make sure that they only accept the best genuine artwork. And they each effectively learn from each other. So the generator's generating more and more examples, let's say fake artwork. The discriminator is trying to separate those out from real artwork and gets better and better at his or her discriminator job by the curator job by discriminating between the two. Based on what's rejected by the discriminator, the generator gets better and better at generating the sort of fake artwork. So this idea of adversarial networks has gained quite a lot of interest in terms of rapidly improving the quality of what's produced. Another example, moving away from the world of art, might be cybersecurity, where there's this constant cat and mouse between the hackers and those are responsible for information security. And as the hackers get better, so do the information security experts. It's the same principle that's mimicked in a generative adversarial network. Another family of network I just briefly wanted to mention is recurrent networks. And these are important where there's contextual information, and particularly sequential information. So each of the examples I presented so far, like for instance the land satellite images or the characters, they were each an example in their own right. They had no reference to what the neural network had seen before. But that's often not the case. You might, if you're looking, for instance, at understanding language, then each word might be heavily influenced by the interpretation of each word will be heavily influenced by the word that came before or the sentence before. And you can capture that idea of sequential dependency in a recurrent neural network. And what's happening here is there are connections from the network, from the output of the network, back to the input. And that's giving that sort of that sequential context. So with every set of new inputs that's being presented, you're also presenting the previous set of output information. And one particular design that's quite popular at the moment is so-called LSTM, long short-term memory. And the principle is the same, that you've got a set of, in this case, more complicated processing neurons, but as well as the input coming in, you've also got the previous output coming in. And if you sort of unravel that through time, which is this is a sort of equivalent representation, you've got input at time 0, producing output at time 0, but that output then becomes one of two inputs, then the next time step, and so forth. So I just want to pause now to summarize where we're at with neural networks. Essentially, neural networks are used for pattern matching. It's effectively what they do, and their uses, I think, overwhelmingly, they're classifiers. If you don't remember anything else about neural networks, classifying is a key thing that they do. But you might also say that they predict, based on a set of inputs that predict a corresponding output. You might say they cluster, particularly the unsupervised networks are good at clustering, recognizing input patterns that are similar to each other. And more generally, you can say they're non-linear mappers. That is to say, they learn to associate sets of inputs with corresponding sets of outputs. I mentioned in the case of convolutional neural networks that they're great at finding the generic primitives. So they find the features in the image, they sidestep for you that problem of pre-processing. And the so-called AlexNet is an example of a pre-trained convolutional neural network. A lot of the computational work has already been done for you, trained on a wide range of different images, and then you can then just train the final steps, the final layers of the neural network, which is very similar to the multi-layered perceptrons that I showed you. I briefly introduced recurrent neural networks for sequential data. And I guess the final point to note is that these so-called deep learning neural networks, these large-scale neural networks, have effectively launched a second wave of enthusiasm for artificial intelligence some 30 years after the first wave during the 1980s, where there was a great deal of excitement around neural network, well, around AI at that time, partly driven by so-called expert systems and knowledge-based systems, and partly driven by the development of those multi-layered perceptrons. So looking back at what we've covered in this first section, tried to contrast the knowledge-based approach, which had very explicit human expertise captured in a computer system, expressed in a very explicit textual form, and contrasted that with the neural networks, where they're reliant on rich sources of data. The more data, the better. And I introduced this sort of the 1980s generation of neural networks, and they've moved on now to so-called deep learning. Well, what I would say about deep learning is that these algorithms are deep in the sense that there are many layers. They are deep in the sense that there's layers of abstraction, but they are not deep in terms of understanding. There is no contextual information at all, and that's one of the things I'll revisit when I talk about bringing together different techniques in a collaborative, cooperative way. So that brings me to the end of part one, more or less on schedule, I'm pleased to say. Just switch on my video and I will stop sharing my screen for the moment. So I hope that was useful to you. Happy to take a question now. If anybody's got any questions they want to raise, I know there's been a few things going by on the chat. Alternatively, before we break for tea, I do believe Bruce wanted to say something by way of his role and introduce the KTN briefly. Is that right? You there, Bruce? Okay, I think we've lost Bruce. So what I will do then is perhaps pause now, or if there's any questions, please feel free.
Could I just ask a question, Adrian?
Sure. Do you want to say your name? I think I recognise your voice, but you should say your name anyway.
Alex Gale from School of Computing. It's about your introductory slides, about what represents AI, and my question is it clear how you can define the boundaries between what we call AI and what is not AI, or is it like a gradual kind of transition between AI and non-AI?
Sure. No, I think the boundaries are very loose. I suppose it's because different technologies have evolved at different times. So yeah, I think well, I'm going to cover genetic algorithms in the next section, which I think fits the general field of AI because they help solve problems which would otherwise not be possible. They're certainly biologically inspired, but whether they're really mimicking human intelligence, I think you'd be hard pressed to say that. So I think there's a very loose boundary around AI. And that's why I think perhaps there's a lot of misinformation around AI, because people tend to know about a specific angle of it, and the broader understanding is sometimes lost. And I guess part of the key message for me today is to think of AI as that broad toolkit. I wouldn't get too hung up on what's pure AI and what's not. For me, I think it's about solving practical problems that would otherwise be really difficult to solve, or would otherwise require some human intervention. Okay, hope that helps.
Thank you.
Okay, well, I think what we should do is have a tea break. I don't know what's happened to Bruce. I know he had a problem connecting or having the sound earlier, so he may have had to drop off altogether. I'll see if he's there when we resume after tea. But according to our schedule, we should be resuming at 2:45. So we've got just over 20 minutes for a tea break. If you wouldn't mind rejoining punctually, please, and then we'll move on to in the next session talk about genetic algorithms, and we'll talk about bringing the whole family of AI techniques together in a complementary way, which is something I'm really quite passionate about. And what I will show you in that section is quite a lot of practical examples of real life uses of AI. So hopefully you'll find that interesting. So I'm going to reshare my screen if I can. There we go. Hopefully that's now sharing and saying that we've got a tea break, and we'll start again at 2:45. See you later.
Adrian, it's Gloria here. I just want to catch up with you. I think Bruce was here earlier on, but then he disappeared. So I don't know whether he will join back or not. Not too sure whether Liz will contact him again.
Yeah, I don't know if you saw on the chat. He was saying that he connected, but he couldn't get his audio to work, or maybe in the video.
Yeah, he joined afterwards. He joined again. I saw him briefly.
Okay.
But I don't know how long he stayed. He did put something else in the chat as well about Kate. KTN is interested in something. Let me have a look. Animal-inspired AI thinking. So yeah, he did join again.
Well, I'll give him another chance at the start of the next section.
Yeah, Liz, are you there?
Yeah, hi.
Yeah, I don't know whether you want to get hold of Bruce to see whether he wants to join.
Well, I can send him an email and just say, if you're here at the end, then, Adrian can introduce you at the very end. Adrian, what time do you think you'll be finished?
Well, I'm planning to stick to the schedule, so the next session is timed for an hour and a half. So that was going to run through till 4:15. There was a bit of Q&A, which we may not need, and then there was a bit of discussion on opportunities around AI. Again, I don't know how far that will go. So I'll finish the sort of formal presenting at 4:15, and then we just go on depending on how much demand there is for discussion.
Okay, I can send Bruce an email and just say if he is available online around that time, then that might be another opportunity to see if he can introduce himself. But if not, then I'm sure there'll be other opportunities.
Yeah, sure. Well, if he's online when we start after the tea break at 2:45, you can certainly say a word then.
Okay.
Oh,
Okay.
another thing, Adrian, just
myself a cup of tea now, if that's all right.
all right. Yeah, I just wonder whether you want to pause the recording or you want to carry on with the recording with the 50-minute break.
I'll pause the recording and start it again later. Yeah, good point.
Yeah, or maybe you just pause.
Okay, we're recording again, and just for the sake of the recording, I'll just show the open screen. So we're going to cover in part 2 genetic algorithms and also lots of practical examples that bring together the wide range of AI techniques. So yeah, I'm often challenged as to, why genetic algorithms are actually part of the AI collection of tools. For me, I think it's because they're practical. They help to solve real challenges that would otherwise be really hard or indeed impossible to tackle. And they do have that link in through to being biologically inspired, which underpins a lot of the AI techniques. So I think that's the reason for including them in there. I also happen to think they're really nifty and neat. But that's just me, I guess. So the key things about genetic algorithms, first of all, they are a population-based type of optimization, and that's I'll explain what that means shortly. But that is distinctive and compared with other forms of optimization. I'm going to describe how they work. I'm going to show you a practical example, another bit of live software. In fact, two examples with live software, one of which is a bit more robust than the other. So we'll see how that goes, and I'll talk about some practical applications. So they are population-based, as I just said, and they use the Darwinian principles of survival of the fittest. So the idea is that you have a collection of individuals, candidate solutions, if you like, each of which is a point in the search space, and each individual's chance of reproduction depends on its fitness. So the fittest survive and reproduce. The offspring have characteristics of their parents, but they're not clones, they're not identical, and those that are better than their parents have more chance of reproducing. Meanwhile, those that are less fit than their parents tend to die away. So just as with Darwinian evolution, the population as a whole evolves towards an optimum. So let's see what that means in a bit more detail. So what you're trying to do with genetic algorithms and optimization in general is to find an optimum combination of variables. So in a simple one-dimensional fitness landscape, as I've drawn here, there are various maxima and minima. So here are some minima that I'm pointing at. So some of these are referred to as local minima because although they are lower than the values around them, there is a more global minimum, assuming that this function is bounded. We're plotting fitness here, so we're actually normally looking for a maximum. So again, there are some local maxima here, and there is one global maximum, again, assuming that this is bounded and there's nothing else beyond. There's a global maximum here. And by and large, what you're trying to do with optimization algorithms is find the global maximum of fitness, and what you're trying to avoid is getting stuck in a local maximum, which many search functions tend to do. In 2 dimensions, it might look like this. So you're looking for the optimum combination of x and y. You're trying to find this global optimum combination of the two, avoiding these local optima, which are obviously suboptimal when you look at the wider landscape. And I will be showing you a little bit later on this precise example. Let's turn to some practical examples. A little later on in this talk, I will talk about a specialist application of AI for controlling a manufacturing process. One part of that is tuning this device called a Langmuir probe. It doesn't really matter what it does, but in case you're curious, it measures electron energy in the plasma. The key point is that it's got 14 different variables, which are represented by these sliders on this screenshot. 7 amplitudes, 7 phases, 14 variables in total. And to tune this device, you've got to find the optimal combination of those 14, which is really hard for a human operator, but really straightforward for a genetic algorithm. This is exactly the sort of thing they're designed to do. Let's look at another practical example. I led a project a few years ago, which involved model helicopters like this one on the screen here. And the idea was to give each of these helicopters some autonomy, and we could have some interesting behaviors by having a handful of them flying together. Here's what they look like in the lab, just to give you a sense of scale. This is what they do. And to actually build a controller for something like this, one of the first challenges is to give it some kind of stability in the air. That's quite a difficult thing to do. What you have to do is tune the parameters of the helicopter. And I'm just going to illustrate that now with this next video. So what we need to do is to tune parameters of the so-called PID controller, proportional integral derivative controller. Don't worry too much about the details, but we wanted to tune those parameters to get the optimal settings. So what I'm going to show you in this next video is that same helicopter, but this time tethered to the workbench, so it can't fly away. But what it can do is swing to the left and right, and we want to adjust its parameters so that it quickly moves to being pointing solidly forward with no swinging to the left and right. And let's see what happens. So right at the start, when we set it going, you see it swinging wildly to the side. Pretty hopeless set of parameters. Okay, so we get the genetic algorithm going after 5 generations, so just a bit of refinement. It's slightly better, but it's still pointing to one side. 14th generation, it's getting a bit better now. As soon as it settles down, it quickly settles down, pointing forward. And finally, when it's fully tuned, it moves swiftly to the forward-facing, stable position. And we've got a graph here showing it being sort of starting off out of tune, as it were, pointing to the left, and then out of tune, pointing to the right. And in each case, the genetic algorithm tuner got it to a pretty close to optimal setting very rapidly. And in each case, the genetic algorithm actually exceeded the performance of the hand tuning. That's just one practical example, just to get you into the feel of what genetic algorithms are for. There are other optimization techniques, things so-called hill climbing and steepest gradient descent. That's all about following the contour landscape, the fitness landscape, if you like. They're all variants of that. Simulated annealing is rather different. That's inspired by the way in which the atoms rearrange themselves in a metal. Somebody's got a microphone open. I'm getting a bit of noise coming back. You might want to close your microphone, please. Thank you. But the key thing about all of those techniques on the screen at the moment is they are all single candidate optimization. That is to say, they start with a certain best guess, and they try to refine that to find an improvement on that. They're constantly trying to improve a guess focus. Okay. Now I don't know if I have the microphone that I can at the moment. Let me just see if I can find that there. Oops, sorry, ignore it. Just trying to take control. Yeah. I'm just got in front of the microphone switched on at the moment. Let's see if I can mute it.
Adrian, I think if you go to participant, you may be able to mute everyone. I have a feeling.
Mute everyone button.
Maybe, yeah, have a look at the participant.
Okay. Okay, sorry, bear with me for a minute. Can't actually see how to do that. I think I found the offending microphone now, so I'll mute that. Okay, hopefully that's made that little difficulty go away. Right, so yeah, so those other techniques are all based on having a single best guess and trying to best guess so far and trying to improve upon it, whereas genetic algorithms are distinct in maintaining a population of candidate solutions. So let's just briefly introduce some terminology of genetic algorithms. Your population of candidate solutions, each one of those candidates is defined by a chromosome. So that defines the characteristics of each candidate solution. and that's made up of a set of component parts, each of which is a gene, and the overall set of genetic material is the genome. The allele is a specific gene value, where each gene, I should say, is if you think of that XY space that I mentioned earlier, X is one gene, Y is the other gene. Together, that makes a very short chromosome. And in fact, my next slide will illustrate that very point. So each chromosome is an individual in the search space. So in my simple XY landscape, if you imagine a point 2,6, X equals 2, Y equals 6, it would be represented by a very simple gene with two values, 2 and 6. But actually, genetic algorithms are binary. The more general phrase of evolutionary algorithms is not necessarily binary, but genetic algorithms are always binary. So, so you'd use the binary representation of 2, which would be with a couple of leading zeros, 1, 0, and the binary representation of 6 would be 0, 1, 1, 0. A slight detailed point now is that in actual fact, for most genetic algorithms, you don't actually use traditional binary code. You tend to use grey code. Don't worry too much about this, but just briefly, the point is that grey code, first of all, it is really spelt with an A. It's not just that I'm using American spelling. It's named after a person, Frank Gray. The key point about grey code is that as you move from one number to the next number, the grey code only changes by 1 bit. So if you look at any of these items in the table, from one number to the next, only 1 bit ever changes. It's rather different with binary code. If you look at this point here, from 7 to 8, every single one of the bits changes. So that means that can be a bit of a disadvantage with the genetic algorithm. It can mean that if you make a small change in the binary code of a genetic algorithm, you could suddenly find yourself with a completely different sort of value. So that's why grey code tends to be favoured. But that's a little detail. So, so my simple example chromosome 26 would look like this in grey code, so slightly different from the binary version. So let's just talk about what the algorithm does, how it works. You start up here, start box generates a random initial population. Size of the population, well, there are many variables in genetic algorithms, so size of population is one. Typically, you might work with populations in the region 30 to 100. That sort of population seems normal. Evaluate the fitness of each individual in the population. Check for some termination condition. You might have a limit on the number of generations, or you might have a target value in mind that you're trying to achieve. Assuming you're not terminating just yet, you choose the fittest individuals, and they will reproduce. They reproduce by a process of crossover. I'll explain what that means in a minute. You can add some diversity to your population by mutation, and then you have a new population that replaces the original one. And you repeat. And because you're selecting the best individuals to reproduce, at each generation, the population tends to migrate towards an optimum. So I'll just briefly mention how that reproduction works. There's various types of crossover, single point crossover being the simplest. So we're reproducing from a pair of chromosomes, the fittest pair, or a fit pair, depending on what your selection criteria are. And you're mixing the genetic material of the two. Now, I've arbitrarily labeled them M and F for male and female, but of course that really has no meaning. But it's two individuals, and I'm swapping genetic material between them, taking a crossover point here, which I'm pointing to in each of them, and swapping the genetic material to produce children, which have characteristics of their parents, but are different. And here's their binary equivalent. And there's variance on that. You can cross over in more than one place. So in this example, there's 2 crossover points here. I'm pointing at one, and here's the second one to give you a different type of crossover. You can have multi-point crossover where there are several crossover points along the material, along the chromosome, and so-called uniform crossover where any particular gene is available for crossover, and it's a matter of chance probability which ones do or do not swap, indicated by my crosses and ticks here. So variants along the idea of swapping genetic material to produce offspring which are different from the parents but share their characteristics. And as I mentioned earlier, mutation is a way of altering individual genes to give you some additional diversity, variety in the population. So I mentioned that the fittest individuals are selected for reproduction. Fitness proportional selection is the traditional way of choosing, which is what it says, I suppose. An individual's selection probability is proportional to its fitness. The fittest have the greatest chance of being selected. And therefore, its number of offspring is equally expected to be proportional to its fitness. And there are a couple of common variants called roulette wheel selection with replacement and stochastic universal selection, or SUS. I'll briefly explain those. So roulette wheel selection with replacement, you have this idea of a roulette wheel and you distribute shares of the roulette wheel according to fitness. Let me go straight to the example. So just suppose in a very simplified example, we have a population of 3. In a real GA genetic algorithm, you'd have many more than that, but just to present the concept. And I'll call them X, Y, and Z, and they've got fitnesses of 1, 4, and 3. You distribute a share of the roulette wheel according to that fitness. So X, having the lowest fitness, has the smallest share. Y, being the fittest, has the largest share. You then spin this kind of imaginary spinner according to a random number, and wherever it stops, that individual is selected for reproduction. And because Y has the greatest share of the roulette wheel, it has the greatest chance of selection. X, conversely, has the smallest chance of selection. And there's some code, computer code, to implement that. If anybody's interested, that's on the slides that you can have a look at and download later. There are some difficulties with that approach. First and foremost, selection variance. There is a statistical chance that the selected distribution might not reflect the fitness. You might, just by chance, keep choosing X, even though it's the least fit example there. And then in general, two of the big problems that you face with genetic algorithms and really drives a lot of the thinking behind selection are these two problems of premature convergence and stalled evolution. Premature convergence is where your selection is too strong early on, which means that you're not exploring the full search space. You're exploiting a few fairly fit individuals, but they may not be the fittest across the whole search space. So in other words, you're running the risk of finding a local optimum. That's through premature convergence. That's when selection is too strong early on. Conversely, selection may be too weak, particularly later on, and you're sort of near the fittest part of the landscape, but you're not getting close to the actual peak. So those are two general difficulties, the premature convergence and stalled evolution. Selection variance is very specific to the roulette wheel selection, and stochastic universal selection is a tweak which overcomes that first problem. Still uses a roulette wheel, but a slightly different model. So, as before, you distribute the roulette wheel according to shares according to fitness, but this time you only spin the wheel once and you have multiple pointers. So for population size 8, you have 8 pointers. And that eliminates the possibility of spinning several times and picking out the least fit each time. This time, you're guaranteed that within rounding errors at least, you'll pick the fittest individuals more often than the less fit ones. So in this example here, C and E are both fitter than A and H. C and E get chosen twice. A gets chosen once. So it it overcomes that particular difficulty. But it's just a tweak. And again, there's pseudocode available on the for download later. And then there's some other things you can do. So-called fitness scaling is designed to tackle those two problems I mentioned of premature convergence and stalled evolution. And the idea is you have a raw fitness called the objective function and a scaled fitness selective function on which you select. And the concept is quite simple, really. If this is your fitness function to the left, early on, you want to avoid premature convergence, so you squash the fitness function. Later on, you might want to make sure you really do zoom in on the peak and you scale. You stretch the fitness function. So that's fitness scaling. And the third technique for selection that I briefly want to cover is tournament selection. Here, there's no roulette wheel. You simply select pairs at random. For each pair, the fittest one between them is selected for reproduction, and you select a handful that way. Noticeably, the least fit individual can never be selected because it will never be able to beat any of the other individuals. So that's another variant. All of that was perhaps a little bit of detail. It was all ways in which you choose the fittest individuals for reproduction. Another variant is elitism, where you can choose one or more fittest individuals and carry them through to the next generation. They are cloned, if you like. So one of the tweaks, one of the features of genetic algorithms, there's loads of different things that you can do to tweak genetic algorithms, and that's really why there's so much that's constantly being published about them. There's more and more little tweaks and tucks that you can do. So I want to go back to that earlier example I gave you of the two-dimensional fitness landscape. I pointed out that you're looking for the best combination of X and Y, and that the global optimum is here. Well, that looks pretty obvious, but there are other fitness functions, like this one, which is the so-called Schweffel function, where it's actually not at all obvious, even in 2 dimensions, where the peak is. And in real life, you'll actually be commonly dealing with many dimensions of fitness. Let me just go back to that one. I've actually got a software demonstration to just show you that in running in real life. So let me pull up my software. So I'm going to show you an example software where we've got exactly the same problem. We've got our 2 local optima and a global optimum. But to make it a little bit harder for the genetic algorithm, I've made this global optimum quite narrow. And let's see how the genetic algorithm works. Hopefully this will give you more of a flavor of how GAs work. Okay, so you should be able to see on your screen now. A little bit. 2 boxes, actually 2 windows. So I'll start at the right-hand side. This kind of blue area here, this is like a contour map representing what I showed you before, the 2-dimensional fitness landscape, just a slightly different representation. We've got 2 broad local optima here, and here's the narrow global optimum, which because I've made it narrow, it makes it slightly hard to find. What I'm going to do is I'm going to set a genetic algorithm running, see if it can find that global optimum. So I've set my genetic algorithm software to go slowly, so hopefully you'll be able to see what's happening. I'll press go now. So if you look at the if you look at the right-hand side here, you'll see these red dots. These are individuals in my population, and they're somewhat clustered around this local optimum. But you can see odd individuals elsewhere because the parents reproduce offspring which are different from the parents. On the right-hand side, you'll see the red line is the fittest example so far, the blue line, the average fitness. Well, you see there's a bit of a jump there in terms of the fittest so far. And what's happened is that some of the individuals now are finding this global optimum. And now all of a sudden, because those individuals are fittest and reproducing, we get more and more individuals close to this global optimum. And it has found, if you look at the graph now on the left-hand side, you can see it, that step change as individuals sort of moved across to that better part of the search landscape. So I hope that was gives you more of a kind of visual feel for how genetic algorithms work. So let me get rid of that now. And so that's the example we've just seen. As I said, there's more complex landscape. I also now want to move on to a real practical example of a genetic algorithm for the rail freight industry. And like all systems, it has to have a good name. So we called ours SECSI, which stands for System for Evolutionary Crew Scheduling with Intelligence. And this is about a genetic algorithm in a very practical domain of scheduling freight trains. And hopefully this will give you a little bit more of a kind of contextual understanding of why they're useful. So we're working with a major rail freight operator. It's actually DB Cargo, who own various other brands than their own across the rail network. And there are various forms of inefficiency that they face, potential inefficiencies. First is to do with contract utilization. So train drivers are paid for a contracted number of hours every year. If they work fewer hours than the contracted hours, they are still paid the contracted hours. If they're required to work longer hours, then they are paid overtime at a higher rate of pay. So if they're if there are unused hours compared with the contract, that is a waste of money to the tune of nearly £3 million a year. If they're used above their contracted hours, that's also an expense to the tune of just over £500,000 per year, meaning a total loss to the company through inefficient contract utilization of £3.5 million per year. Okay, and that's just one form of inefficiency. Let's look at another, which is to do with the actual practicalities of getting drivers to the right place at the right time. Let's consider the case shown in this map of a driver who's got 3 jobs lined up for their shift, indicated by these black lines between towns and cities. They also have a home depot. This driver is based at the Oxford depot. So at the start of the shift, the first thing they've got to do is get from Oxford the first train that they're going to drive. And they'll do that by taking a passenger train from Oxford to Bristol. So it's the first thing they do, and they're being paid from the moment they leave their home depot, riding a passenger train, get to Bristol in good time to drive the freight train from Bristol to Reading. Then they pick up another freight train from Reading to Stevenage, and then another train from Stevenage to Cambridge. That's all good, they tie in nicely. Then the next job after Cambridge is from Milton Keynes, or Bletchley, I think more precisely, Bletchley to Coventry. Now to get across to Milton Keynes, they could catch a passenger train, but the only passenger route is via London, and that would get them there too late. So what they'd actually do in practice, and this happens a lot, is they would take a taxi from Cambridge to Bletchley or Milton Keynes to take the next leg. And that's an additional expense. They can then drive the train to Coventry. When they get to Coventry, they've got to get home, back to their home depot, and it's too late for a passenger service. So they would need to take another taxi at another expense. So if you look at that schedule for that driver for the day, you'll see that there's expense in terms of taxi fares. You'll also notice that overall, the amount of time they've been driving the train during that shift is less than 50% of the time for which they're being paid. So there are inefficiencies in there. But it's a complicated problem. This shift pattern is called a diagram. There's a maximum that's allowed. There's a minimum, or at least there's a minimum for which they'll be paid. You can schedule a driver to have a shift of less than 4 hours, but you still pay them for 4 hours. There's there's a sort of there's a maximum continuous driving time without a break, and there's a maximum driving time in total on the shift. 8 hours for the total, 3 hours maximum without a break, and there's a minimum break time. So that's quite some complicated constraints on the schedule. Those are hard constraints, and then there are so-called soft constraints, which is things you'd like to maximize or minimize. You'd like to maximize the proportion of time they're driving the train, so-called throttle time. You'd like to minimize the number of taxi trips or passenger train trips, etc. And there's a complex network. This is what it looks like. 550 freight trains per day, 3,000 legs, 1,240 drivers in 39 depots. So it's a complicated task. But we built a genetic algorithm that looks, this is a screenshot. I am going to try running this live, but it may not work, but this is the screenshot in case it doesn't. And you'll see that what we can choose what we want to optimize, but typically we're trying to optimize this thing, the cost function. So this, because it's a cost, we're trying to minimize it rather than maximize it. Oops, excuse me. But equally, there are other factors like the taxi cost. We could be focused on the taxi cost. We could be focused on the number of diagrams, that's just the number of shifts, if you like. But we're focusing on the total cost. Right, I'm going to see if it's a bit unreliable, this software, but I'll see if I can run that for you. So this is the software, and I'm just going to run it now, hopefully. Okay, so what you'll see here is some evolving graphs through time as the shift is getting, the schedule rather for the drivers is getting more and more efficient. And if you look at that second graph down, the cost function graph here, you see that cost function going down as the genetic algorithm is doing its task. Okay, and as that's running, I won't save that. As that was running, you see some of these factors going down, taxi costs going down, number of deadheads, etc. So now that away. So that was the screenshot. And now let's look at what that means in practice. So the manual schedulers are pretty good in terms of designing the schedules, but our system, Sexy, is actually better. And not only is it better, but it runs in just less than a minute, as you've just seen, as opposed to being quite a laborious manual task. We were able to, with Sexy to come up with improvements across numbers of drivers payments, taxi costs, and daily cost of the schedules, save about £5,000 every day, which is worthwhile contribution, on not to mention the cost of the labour saving of actually drawing up the schedule in the first place. So to summarise the genetic algorithms, they're population-based form of optimization. Each individual is a point in the search space, and it's based on survival of the fittest, with an individual's chance of reproduction depending on its fitness. We talked about crossover and mutation and the way that's used to introduce diversity into the population so that it explores the full range of possibilities. And that's the key there. The cliche is exploration before exploitation. So with a genetic algorithm, because of this diversity, it can explore the whole search space before exploiting the global optimum. The things that can go wrong are if the selection is too strong, you prematurely converge on a local optimum. Conversely, if the selection is too weak, evolution stalls and you don't get close to that optimal position. And there are very many practical applications, of which I hope I have shown you a few. So, thank you. That was the coverage of genetic algorithms. The final section is going to be on hybrid systems, bringing this all together for real-world practical genetic algorithms. Does anybody have any queries before I move on to the hybrid systems? Okay, I hope people are still listening. That's
Adrian, sorry, I think Pete asked a question in the chat.
What was this? So in that example that I was running, I used SUS, which is the Stochastic Universal Selection. That particular software I was running, which incidentally you can download from my website and play with to your heart's content. It is freely available. It was developed by the Open University, who I used to work for, and they have given me permission to share it with everyone. So please do try it for yourself. But to answer your question, it's stochastic universal selection. That was the second variant of the roulette wheel that I mentioned to you, where there are multiple spinners all spun at the same time. But with that software, you can all the standard techniques are in there if you want to try them for yourself. Obviously, I've run it a few times and found that the particular combination that I was using there gave a nice demonstration of being able to see it struggling a little bit early on and then moving across to to find the global optimum.
Adrian,
Hi.
What is actually the impact of choosing the initial population on the performance of the algorithm? If you choose, for instance, the wrong population, how will it affect the algorithm in obtaining, in reaching or the optimum or the minimum of a problem?
Yeah, no, it's a good question. So the normal way you start is with a random selection of individuals, and as you suggest, some of the sometimes you might get a more favourable initial population than others. If the genetic algorithm has been well designed, it should be able to cope with a very poor initial population and rapidly start to evolve towards a fitter population. But if you're ever presenting genetic algorithm results, you do have to take into account the exact point that you've made. So what you would typically do is show the average result over many runs, and you should also point out if occasionally it was particularly poor. So you're looking at the any outliers, and you're looking at an overall average performance if you're evaluating your genetic algorithm. But if you've got a good one, you would hope that there are a few outliers and that it consistently finds an optimal or near optimal solution.
Thank you.
Okay, if there are no further questions, I shall move on to the final section, which is about hybrid systems for practical AI. Now, that's just, when I say hybrid, I mean mixed mode, complementary techniques. So I'll just sort of very briefly recap with my Venn diagram of techniques that we started with. Then I'll give you 5 reasons for hybrids, each of which I will illustrate with a practical example, or actually more than one practical example. And my conclusion will be that if you go back to that spectrum of intelligence that I started with, I think to bridge that spectrum really requires a mixture of different techniques. So just a reminder of where we started this workshop this afternoon, with this toolkit of AI techniques, broadly broken down into knowledge-based, explicit textual representations of expertise, and the computational intelligence, which is data-driven. So why hybrids? Well, I'm going to argue for 5 different justifications. I think the first one, multifaceted problems, and perhaps the second one as well, are overwhelmingly the most important 2 amongst them, but I will highlight all 5. So starting with multifaceted problems, and I'm going to, before getting onto the examples here, I'm going to point to the underlying techniques that we're using. So for many years, I've had an interest in multi-agent systems, where you break down a problem into subtasks, tasks of the overall problem, each of which requires a specialist software agent to tackle it. So when you look at the overall broad problem, you're effectively modeling a team rather than an individual. So remember, the definition of AI at the start was about mimicking human behavior, but in this case of the multi-agent systems, you're perhaps mimicking a team of humans working collaboratively. There are many different ways in which you can design multi-agent systems, but I've been interested for a long time in the so-called Blackboard architecture. Incidentally, if anybody's used Blackboard, the virtual learning environment, it has nothing to do with that. It's just a coincidental name. But other forms of multi-agent framework are available. This just happens to be one that works quite nicely for me. Quite an old architecture, which has sort of had a bit of a resurgence of interest. This is what the model looks like. It's meant to mimic a group of individuals, expert individuals gathered around a blackboard, or you might say a whiteboard, each of which has a marker pen and an eraser. One of them will pose a problem on the board. If any other one of the experts gathered around can see a way to contribute to solving that problem, they will add their contribution to the board, to the whiteboard or blackboard, so a solution evolves. That's the model. We've built a software system called DARBS, Distributed Algorithmic and Rule-Based Blackboard System. And here, those agents are now software modules or agents, each of which uses whatever technique it needs for its specific task, and the blackboard is an area of shared memory. We use the concept of opportunism, which is to say that those agents carry out their function whenever they can. Would typically be triggered by seeing something on the blackboard, and they'd say, ah, I know about that, I'll do my function and add what I know to the blackboard. And hopefully this will become a bit clearer when I show you some actual examples. But the agents can be whatever you want. So with DARBS, it's just a framework. It is freely available. And we are actually, I do need to upload the newer version to the website, but it is freely available. And the agents can be whatever technique you want. So typically we'll be mixing rule-based, knowledge-based agents with specialized dedicated software modules, plus genetic algorithms, plus neural networks, plus whatever else you want. So to give you some specific examples, I'm going to highlight 3 examples actually of this concept of multifaceted problems, starting with controlling a process called plasma deposition. I'll then look at briefly at a couple of other examples. But plasma deposition is a complex manufacturing process. You really don't need to worry too much about the details, but it's used for laying down thin films on the surface of components. We were using, we were depositing diamond-like carbon, which is, say, layers of artificial diamond, a process used in the semiconductor industry and some high-value manufacturing mechanical components. But the plasma in this context is a low-pressure ionized gas. If you get the conditions right, then the ions from the gas deposit on a specimen, where I'm pointing here in the middle, to form a nice thin film of neutral atoms. But the key point is that it's quite difficult to control. There are various things you can measure, which I've highlighted in blue, and various things you can control, which I've highlighted in red. Unfortunately, they're not the same as each other, so various inferences have to be made as to what you need to control in order to get the response you're looking for and the thing you're measuring. This is what the equipment looks like in real life on the laboratory scale, and we built an AI system to control the whole plasma deposition process from the pumps through to managing the plasma itself to shutting it down. That's what the plasma looks like through the window. If you look at the window inside there, that's what it will look like when the plasma is fired up. And I have a short video to show you of this in operation. There is some sound which you may or may not be able to pick up. Doesn't matter too much, but there's some whirring noise in the background at the moment, which is the pumps going, and then there's some clicking noises as the pumps click in. You may have heard that. And what you're seeing on the screen there is a pump controlling agent, specific task, now fired up the plasma, and there are some agents mentioned that. Specifically, there's a fuzzy logic agent, which I'm going to show you shortly, which maintains the some of those electrical parameters. And finally, you've got something you may have seen before, actually, which is the Langmuir probe. Remember, I mentioned that as an optimization problem, which looked just like this. So that was that problem I mentioned earlier. Just one part of this overall team problem of controlling the plasma deposition is keeping this Langmuir probe, which measures the electron energy, keeping that tuned. And that's using a genetic algorithm. I mentioned the fuzzy logic controller for the electrical parameters. And what that's doing is maintaining an electrical parameter, which I'm pointing out in the bottom graph here, called DC bias. It's trying to maintain it at minus 400 volts. And what's going on in these graphs is every time it gets close to it, wherever you see a vertical line, we've come along and deliberately knocked it off its set point. And every time it adjusts these other things, pressure and RF power, to bring the controlled variable, DC bias, back to its set point. Smoothly does it, and then we keep knocking it off to make life difficult for it, and every time it uses fuzzy logic to bring it smoothly back to where it's supposed to be. So you've got all these different collaborating modules. You've got this fuzzy logic module managing the electrical parameters. You've got your Langmuir probe for tuning. So you've got the tuner using the genetic algorithm. You've got the rules controlling the pumping systems and so forth. So I think a great example of a multifaceted problem requiring this kind of team approach. I'll skip the process optimization. Another example using the same underlying DARB software was working with BT to manage and control their communications network. So this is what the network looked like a few years ago, and there's a control center at a place called Oswestry, around here somewhere near the Welsh border. And what we did was build a control system to make manual interventions into the network, and that's what's shown on this rather busy screenshot here. But what you're seeing on this screenshot is lots of different windows popped up. Each window is a manual intervention. So what happens, what the controllers do at the control center at Oswestry is they're constantly managing the performance of the network, looking for points of congestion, loss of service, and taking corrective actions. And we built a multi-agent system to do just that, where each agent was looking at a specific control action that it was able to take based on what the information it could see on the blackboard. So towards the top left here, we've got on a particular local route between the trunk centre, Manchester, and the local exchange, it's introducing something called call gapping, which is a way of restricting traffic on that route. Elsewhere, we've got something called trunk reservation factor on a long distance trunk route between major exchanges. Again, managing controlling traffic there. Elsewhere, we've got other control actions, perhaps the most complex ones going on in this bigger window here, where it's setting new secondary routes. So what this is for every connection between exchanges, there is a primary route, and there's also a secondary route, which is a kind of alternative way around. So by dynamically creating new secondary routes, you can find new real-time solutions to any points of congestion or loss of service. And this was what was being done in real time here. And my third and final example of a multifaceted problem is quite recent work, actually. This is from a PhD student who completed in the last 6 months or so. And she was building a multi-agent system for automated umpiring. This was an automated umpire for table tennis. And unlike sort of VAR that you see for football, or Hawkeye that you see in elite tennis, this was nothing to do with elite sport. This was to do with providing an umpiring aid for the amateur game that might happen in your local town hall or gymnasium, where you can't afford expensive equipment. This is based on just 4 relatively low-cost video cameras, which were tracking the ball against a complicated background, and it relied on on agents to do specific tasks to do with tracking and following those the ball. There's ball detection agents, there's a multi-view managing agent, there's a trajectory construction agent, feature detection agents, state detection agents, all to do with making sure that the passage of the game was being monitored, and then actually the rules of the game were quite simple to overlay on top of that as a rule-based system layered on top of the ball following algorithms. But another example of a multifaceted problem. I'm going to move on now to talk about my second justification for hybrids, which I've called clarification and verification. And I'm going to start by revisiting something I showed you earlier with the neural networks and postcode recognition, because I already only gave you half the story there when we were looking at the neural networks, and I'm also going to look at ultrasonic image interpretation. So postcode recognition, as I mentioned earlier when we were talking about setting up the scene about AI. This was a classic AI problem until it's effectively been solved, and now people tend to think of AI as something more futuristic. But for me, this is AI that's out there in practical use in the real world. So here's the postcode of Peterhouse College in Cambridge, where I previously presented this workshop. And there's the postcode written in different forms of handwriting. And it is quite a challenge to build a system that can accurately read those postcodes. So you saw earlier that you could build a neural network to recognize individual characters. And we ran a demonstration using this small character set and trained it on a simple neural network like this multi-layered perceptron to generate recognition of each of those characters, from which you effectively construct a postcode. But you don't have to just stop there. There's more information at your disposal than just the recognition of each individual character. So first and foremost, there are only 7 valid postcode formats, as defined in the postcode guide of 1993. And overwhelmingly 2 of those are more common than the others, which are these, the third and the fourth one, which have 1052 and 1482 respectively, variants of the outcodes, which is the second part of the postcode. So many more examples of those than the other formats. But nonetheless, either way, no matter how you look at it, there's only 7 valid formats in terms of the combination of alpha characters and numerical characters. And if you look at the final example, there's only 1 postcode of that format, so it's a bit of an outlier. That's just the formerly used by the National Gyro Bank. I think it's now reserved for some other government purpose. So 6 real categories of postcodes. So if your prototypical postcode from the neural network doesn't fit one of these templates, then you know you've got something not right with your output from the neural networks. That's an initial check. But it doesn't stop there. There is more beside. There are a whole stack of rules which you can easily put in a rule-based system to overlay on top of your neural network. So here are some examples. Again, from the postcode guide, the letter J is not used in either of the first 2 alpha positions. So if your neural network says there is a letter J, then it's got its classification wrong, or it's an erroneous postcode as written by the person who wrote the envelope. Either way, it's not a valid postcode. The letters Q, V, and X are not used in the first alpha position, and so forth. Letters I and Z are not used in the second alpha position, except in that one unusual postcode. Only letters to appear in the third position are those, the only letters to appear in the fourth position are these, and so on. So there are this whole set of rules which are complementary to what's coming out of the neural network. And in fact, I used to set as an Open University student assignment to build a neural network to classify the characters and a knowledge-based system to check and verify them. Now I want to move on to something a bit more sort of challenging, as it were, and a real world practical example. Quite early work, this actually, but I still think it's quite important in terms of illustrating this use of using one technique to validate or verify another. So here we've got the problem of interpreting ultrasonic images. Ultrasonic images from a steel plate, it's a different type of imaging methodology than medical ultrasonics. What you do is you scan a set of transducers across the surface of the component backwards and forwards, and with each pass it produces an image known as a C-scan, which is a cross-section through that component. In this case, it's a slab with a weld down the middle, and that weld has some defects in it, which we're hoping to pick up and detect. So each pass across the surface generates an image like this. Where each dot represents, is a so-called indication, it represents a pulse echo that's been detected. So you're pinging pulses into this, ultrasonic pulses into the specimen, listening for an echo, and according to the delay in receiving that echo, the longer the delay, the deeper into the specimen you assume the source of the reflection to be. So you build up an image like this where each dot represents the assumed origin of a reflection. Each dot has associated with it, as well as the position that you can see, it also has an intensity and an identifier for which of the transducers pointing in different directions has detected it. So interpreting an image like that is quite challenging, but we were able to build a multi-agent system to do just that. So the first task is to pick out the key features, a bit like the primitives that I mentioned in the case of characters. So here the primitives are obtained by finding lines of indications. And that was done using a Huff transform. So we have a specialist agent, the Huff transform agent, which picks out these lines of indications. There's a rule-based agent is also picking out some of the identifiable features like this back wall echo here, the back of the specimen. And this, although it's not labeled in the screenshot, is identified as an artifact due to reverberation. So some pre-filtering is then applied using that rule-based approach to give you something that looks like this. And we can then go on and use further rule to identify these areas of intersection being the key areas of interest. And this is where it gets really interesting. These are the areas of interest, and they can be classified using a neural network. The neural network is taking in features of around these areas. It's looking at the way in which the intensity varies along these lines through the area of interest. It's looking at the directionality. It's looking at it's looking at the characteristic signature of the ultrasound through those areas of intersection. A few variables that are put into a neural network. And the neural network has, in this case, it says here, network classification associated with smooth crack. And what it's saying, the neural network reckons that each of these boxes is a crack tip. So that's the neural network classification. But how can you be sure that that's accurate? And that's where the idea of using a rule-based system, knowledge-based system that verifies that comes into its own. So in this case, that classification was validated and verified. And the way it was done with a rule-based system then went back and said, treated that as a hypothesis, said if there's a crack there, then when I look at this image, if there's a crack running here, I would expect to see a shadow in the back wall echo down here, and that was indeed seen. Further, we now have an explanation for these features off to the left. These are now consistent with being artifacts produced by multiple reflections between the crack tips, creating the illusion of features deeper into the specimen over here. So we've now got a validation through the application of other sources of explicit expertise for our neural network classification. So that's my second justification for hybrids, is using one technique to validate or justify another. I'll quickly now run through the other three. The first one is what I've called capability enhancement, using one technique to enhance another. In this case, cascading neural networks for detecting oral cancer. So if anybody's squeamish, please look away now. Some images of oral ulcers are about to appear. The top two are different types of RAS, that's recurrent aphthous stomatitis, minor and major. They are harmless ulcers that we all see from time to time. Lichen planus is a feature that is not harmful in its own right, but should be monitored. And then in the bottom right, we've got an example of a cancerous ulcer. So mouth ulcers, a mouth cancer rather, is quite nasty. Mouth ulcers are common. Thankfully, it's quite rare to have a cancerous one, but the cancerous ones do need to be detected early, otherwise they can be fatal. So the vision here was that a dentist would routinely point a camera at these ulcers and get a quick preliminary diagnosis as to which ones are suspect and might require a biopsy and possible treatment. So this was done using traditional multi-layered perceptrons and Cahonan networks that I showed you earlier. I would really like to revisit this with a richer data set. We were hamstrung by limited data, so we didn't have a large enough data set. We were doing our best with the simple neural networks, and we still got some promising results. So I'd really like to revisit with a bigger data set and a convolutional neural network. But nonetheless, we used a multi-layered perceptron, which looked like this, Cahonan network, which looked like this, and we were getting some pretty good clustering with the Cahonan network of the cancerous group, but we were not getting an accurate multi-way classification of all the different types, which is what you really need to have something that's robust. And what we actually found was that the best combination was achieved through a hierarchical combination of different networks. We'd have a Cahonan network to cluster together the cancerous ulcers, a second Cahonan network then to separate out the lichen planus from the remaining ones, and then the multi-layered perceptron to classify the others. And we found just through experimentation that was the best approach, was this combination of different techniques, so one technique enhancing another. My fourth justification for hybrids is parameter setting, and we've already touched on a bit of this. First of all, the PID controller, proportional integral derivative controller for the helicopter control, you may remember, that used a genetic algorithm for setting the parameters of a PID controller. So the PID controller is one technique, the genetic algorithm is another. So you're using one technique to set the parameters of another. I won't repeat that. I won't go into that again. Let's move on to the rail freight scheduling. Now, I showed you the genetic algorithm, but there's something else beyond that that I haven't shown you yet. And that is that we've used a fuzzy logic controller to enhance that genetic algorithm in real time. So here's our rail freight problem that we've seen before. Genetic algorithm, I've set that up before. You remember you've got this idea of a population, you select the fittest, you reproduce through crossover, you add diversity through mutation, and you have a new population. I also mentioned that there are loads of things you can control and adjust in a genetic algorithm. So what we're doing with our example, with the example we showed earlier, is we're introducing in real time some automated parameter adjustment. And what we're doing is introducing effectively a fuzzy logic step where we're monitoring the performance of the genetic algorithm, seeing how it's working in real time and adjusting its parameters. And these are what some of the fuzzy rules look like. So we're monitoring the performance of the genetic algorithm through its convergence measure, CM. We're also measuring UN, which is the cycle since the last improvement, and we're also measuring VF, which is the variation, the fitness variance. 3 parameters of how the GA is performing, and we're adjusting the mutation probability and the crossover probability according to what we see. So if we're getting low convergence, so it's not evolving effectively, then we increase the diversity by raising those mutation and crossover rates, and so forth. Conversely, if it's converging too quickly, then we can slow it down. So adjusting those to compensate, if you like, for those problems I mentioned earlier of premature convergence and stalled evolution. So that's adaptive mutation in real time, tweaking the parameters of the genetic algorithm, and the results are quite impressive. So if you start by looking at the blue line, this is when we used our standard genetic algorithm for the rail freight scheduling problem. And as you'd expect, the fitness rapidly goes down as you evolve from a rather poor initial starting set of schedules. So it rapidly improves those schedules, lowers the cost of those schedules through the blue line. But when we introduce our fuzzy logic controlled genetic algorithm, which is the red line, you see we get to a better, lower cost solution more rapidly in fewer iterations. So there's I think a good example of using one technique, fuzzy logic, to adjust the parameters of another. My fifth and final category of hybrid is what I've called divide and conquer. I'm going to specifically talk about the problem of image registration, which is quite a narrow, specific problem, which is, if you like, a subtask of wider problems. And in that domain, it does sort of create the idea of nested agents. So you might have a problem of image registration as a subtask as within a broader problem, but it's complex enough that it needs its own multiple agents. So you have this idea of multi-agent system. I'm going to show you in a moment some examples in the medical domain and also in the manufacturing domain. And we're focusing on the specific task of image registration, and that image registration task is an agent, but it uses multiple agents within it. So let's start with the medical domain, where it would be really useful to superimpose different forms, different modalities of image. So here we've got a visual and thermal image that we're trying to superimpose. The visual image top left, thermal image top right. If you just put one on top of the other, you end up with this rather mismatched image in the bottom right. Because when you have two modalities, they're never properly aligned. One is always going to be slightly distorted relative to the other, slightly translated, slight different rotational orientation, etc. They never quite match. That is the problem of image registration. The checkerboard effect towards the left is representative of the fact that what we did to solve this problem was to break those images down into component parts and give each part to an agent, this sort of sub-agent, if you like, of the overall image registration agent. So each sub-agent was working on a different part of the image, and then the whole lot was brought together. And these are the results of using our multi-agent image registration system. We've now got a nicely registered image, but what you're doing is distorting one image relative to the other. And it's doing it by working in different segments of the image and then putting it all together. So that's image registration in the medical domain, but it occurs in all sorts of domains. So here's an issue for a company that makes screen printed bottles, screen printed packaging. And they wanted to detect defects in the screen printing. So in this case, they were making high-end shampoo bottles, and the client is, because it's a high-end quality shampoo, wants a high-end quality packaging. So minor defects in the quality of the print would lead to rejects. So in this case, this is what the logo is supposed to look like, but you might, for instance, get these defects here with a little bit of the ink is missing. And the aim was to try and detect those automatically on the production line. And the company thought that what they could do in principle was simply have a sort of perfect template image and subtract that from a live video feed of images of printed bottles coming off the production line. Subtract one from the other. If there's a difference between them, that means a defect, which is fine in principle, but it ignores the problem of image registration. You're always going to have a challenge of registering those images, distorting one relative to the other so that they're perfectly aligned. So we used our multi-agent system to do just that, to carry out that image registration. We also needed a bit of rule-based expertise to pick out edge effects like this and then identify the defect. So again, using a multi-agent approach, we're able to identify the defects in real time. So I'm coming towards the end. Let's just wrap up on why hybrids. Hopefully I've given you 5 examples, 5 justifications. I think the first 2 are really important. Multifaceted problems, most practical problems, have many different aspects which require different techniques. Each technique is quite narrow in what it can achieve, but together, those techniques working together can solve a broader problem. I also talked about clarification and verification, using one technique to validate and verify the conclusion of another. And I showed you postcode recognition and the ultrasonic images. Talked about capability enhancement, using one technique to enhance another, and parameter setting, using one technique to set the parameters of another. And the fuzzy logic controller for the rail freight scheduling, I thought was quite a good example of how the fuzzy logic control could enhance the genetic algorithm by tweaking its parameters. And then finally, we saw divide and conquer, breaking down a problem using multiple agents. So towards the start of this presentation, I showed you this spectrum of intelligence. I talked about how early successes in AI tended to be at the top end of that spectrum of intelligence, dealing with specialized expertise in professional domains like law and medicine and particular sciences. At the low end, regulation, reaction, coordination, sort of thing that robots have been doing for a few decades now. And progressively, with things like convolutional neural networks, we're starting to see progress in the middle in terms of common sense, perception, vision, language, and so forth. But I showed you that picture of the tank at the start. I told you about getting a sense of context there. I think that's a great example of where using a convolutional neural network might be able to get you to recognize the tank, but you'd also need to overlay on top of that a rule-based system to recognize the context, that it's got civilians on it, that it's in a street in London, that it's not in a military context. I sometimes use the example of the driverless cars as well. So the driverless cars would learn from the experience, their experiences of learning to recognize features in the road, and indeed that can be a pooled experience that the whole fleet learns from, not just an individual car. But at the same time, you wouldn't want it to learn the rules of the road by observing what other road users are doing. You can tell it the rules of the road, give it an explicit, digitized, rule-based version of the highway code, if you like. So, by way of conclusion, I see a future in which the spectrum of intelligence is bridged with complementary AI techniques, and I think we're making great progress there. My mantra, since there is such a focus at the moment on the deep learning, the large-scale neural networks, the big data, my message is don't rely on data alone. I think knowledge is required. It's still required. It may not be quite so fashionable as it was, but it's required to provide context and understanding. I mentioned DARBS, the distributed algorithmic and rule-based Blackboard system. It is available to the open source community. I'm looking for real-world applications. I'm about to upload a new version of it from my website, so maybe don't download the current version, but there will be a new version there soon. Talked right at the start about the question of the human in the loop. Something to bear in mind, you're either, it's a design decision really, whether AI is used to make decisions autonomously, as we saw with the plasma deposition. That was an AI controller for the plasma deposition system. You set it going and it would do the whole process. Alternatively, AI is often used with the human in the loop, That's often how it's seen in the medical domain. People still want the input from the medical practitioners, but there's great enthusiasm amongst the medical clinicians to have AI there to guide, advise, to streamline some of the decision making in areas like interpreting radiograms, ultrasonograms, etc. There are lots of issues that need to be borne in mind: cybersecurity, trust in the system, the quality of the data. If you're using machine learning, it's only going to be learned based on the quality of the data, and there could easily be contextual assumptions around that data, maybe taken from a narrow population set. You need to be thinking all the time about that. Issues about legal accountability, about when AI is used, who's responsible for what it decides to do. Is it you who's put it into practice, or is it whoever's built it? And that's linked to ethical questions. All these issues do need to be addressed. And I would say that whilst AI is sort of in its infancy, really, and it's been around since arguably 1950, but in terms of actually starting to make real inroads into everyday life, it's still in its infancy, and we should be having those ethical and legal accountability discussions now. Of course, I've got to promote the book. So my book has been published in 3 editions. The 4th edition is coming out next year, so I'm working on that at the moment. I need to complete the manuscript this calendar year, so look out for that. I do maintain a toolkit of AI techniques on my website, so do look out for that, and I will be adding new things, particularly as I work towards that 4th edition. I think I'll skip the next thing I was going to show and just end up with a whole list of acknowledgements. So pretty much all the examples I showed you here were based on the work of other people, PhD students sometimes, or research associates that I've worked with over the years, or fellow academics that I've worked with over the years. So I'd like to thank them all, and I'd like to thank you for sticking with it for this rather long workshop. Thank you very much for listening.